Today I'll be solving problems related to the concept of energy. This is the first problem. So we have this force shown with the blue line. It changes with position, horizontal position. So it's not a constant force. Question is, find the work done by this force over the distance x equals 0 to x equals 15, from here to here. Okay, so this is pretty easy to solve if you know that work done by a force is just the area under the force versus position graph. Okay, so we can consider this as three distinct parts, positions. Like first this part, work done up to 5 seconds, and then 5 to 10 seconds, and then 10 to 15 seconds. So the area in this part is 15 Newton meter divided by 2. Work done in this part will be 15 Newton meter or joule. And this part, again, 5 times 3, okay? So it's the same as this part. And here is the calculation, okay, as I described. So this work done is 30 joules. So the purpose of this example was to demonstrate you to work with graphs, okay, for forces. Now the next problem. So the potential energy of a system of two particles separated by a distance r is given by this expression, A over r, where A is constant. Find the radial force Fr that each particle exerts on each other. So I'm not quite sure if I lectured this. Maybe it was the very last slide, okay? I think I did lecture. But anyway, I will continue. So you can check. If I didn't lecture it already, then I will in the next hour on Monday. So this is the potential energy. Okay, as you see, it's a radial. It has a radial dependence. So it just depends on the radial distance. Yani 3 boyutta iki cismin sadece arasındaki mesafe ne? Radyal mesafe diyoruz buna. O sadece o mesafeye bağlı. Bir de sabit var. There is a constant. A is a constant. So find the radial force Fr that each particle exerts on each other. Again, a very easy question. We will be using just this formula, okay, which related work dr. Just imagine this dr on the left hand side, then it is dr Fr, okay, work. On the right hand side, we have minus du. You can say that it's like delta u. So this equation says that work done by that force, okay, is equal to negative change in the potential energy of the system, okay. There's a very important nuance with this equation, and when you will use it, this force must be internal force, okay. That force must be part of the system. So there must be potential energy associated with that force, okay? Therefore, for this problem, this equation is automatically correct because we are given the potential energy and we are asked to find the associated internal force, okay? So I repeat this expression, okay, and its other forms like d over del over del x, del over del y, etc. They are correct for internal forces, okay, for forces for which there is a related potential energy, okay. So it's as simple as this. You just differentiate the potential energy with respect to the position, and there's a negative sign. So here it is. A divided by r square. The physical meaning of this example is, as you see, it's a positive. It has a positive direction. It increases with position. It's inverse R square. It has an inverse R square dependence, okay? So this is both the form for gravitational force and electric force. If some of you are also taking physics too, or remember when, from the times when I took it, this is just the potential, electric potential created by a unit charge, in fact, okay? And similarly, for, potential due to gravity. So next one, okay. We have a single conservative force, okay, that acts on a 5 kilogram particle, capital M, within a system due to its interaction with the rest of the system. See, this is a very important expression. Within a system due to its interaction with the rest of the system. We have this force, okay. It acts on the 5 kilogram particle within a system due to its interaction with the rest of the system. This means that this force is part of the system, okay? System is particle plus this force. Therefore, there must be, for example, a potential energy associated with this force, okay? Moreover, and also, since this is a conservative force, another important thing. So, we have the given force equation, Fx, 2x plus 4, and the particle has a displacement from x equals 1 meter to 5 meters. Okay, so calculate the work done by this force on the particle. Okay, it's just asking to calculate the work. That's it. No mention of potential energy, no nothing. We will just calculate the work. So a graphic representation of what's happening. Object of mass 5 kilograms. Force, okay, which is position dependent. It gets stronger the more to the right and also to the left you get. And it's an internal force, it's part of the system. That's how this system is defined, okay? Yani burada sistem öyle tanımlanmış. Sistemler şöyle tanımlanır, böyle tanımlanır diye bir şey yok. Nasıl işinize gelirse, hangi hesap kolayınıza geliyorsa öyle tanıyorsunuz. Hepsinde sonuç aynı çıkmak zorunda. Now, let's calculate the work. So this is, work is F dx, okay? Force, displacement. Since force is not constant, we must integrate over infinitesimal displacements. It's 40 joules. If you like, you can also graph it and then calculate it. I guess 2x artı 4, evet, grafikte de çıkar herhalde. Okay, what else? So part B, the change in the potential energy of the system, okay? It is trivial if you know what you're doing. So if this is the work done by the force on this object, and if this is an internal force, then here the same thing is going on, okay? Just move this dr to the left-hand side. You have internal work equals negative of change in potential energy. Negative of internal work is equal to change in the potential energy, okay? I can write this because this is an internal force, because this is part of the system, okay? Therefore, change in the potential energy is minus 40 joules. If you like, you can imagine like this. Let's say maybe this force is like a spring, okay? So it pushed the object, okay? Did this much of work. Work is energy transfer, okay? When this much of work is done on this object, it will speed up. It will gain some kinetic energy, okay? So its kinetic energy increases. Where does this energy come from? Since it's an internal force, then potential energy must decrease, okay? That's the balance of things. This system is also isolated, okay? only thing there is in this part of the universe is this internal force and the object. There's nothing else. So I hope you can follow what's going on. This is a change in potential energy minus the work, 40 joules. Part C says that find the kinetic energy particle has at 5 meters if its speed is 3 meters per second at x equals 1 meter. Right here. Okay, let's find. To find it, we will use the work kinetic energy theorem, which says that if there is no effect of a force on an object other than the kinetic energy change, then that work will become the kinetic energy of that object. So here it is. This is the final kinetic energy. It will be the initial one plus the work done on it. Okay. Initial kinetic energy will be calculated using this the velocity at the initial position, which is 1 meter right here. This will be that kinetic energy, and this will be the work done. Okay, as you see, we calculated it from 1 meter to 5 meters, 1 meter to 5 meters. So that's the work done on this object. So the sum is 62.5 joule. Şeyi bu. 5. metreye ulaştığındaki kinetik enerjisi bu arkadaşlar. So okay, next question. A force acting on a particle moving in the xy plane, it's in 2 dimensions, is given by this expression. 2yi plus x squared j. So it's a function of both, it's a function of position. It's not constant. Here f is in newtons and x and y are in meters, okay. Now the particle moves from the origin to a final position having coordinates x equals 5 and y equals 5 meters. The particle starts moving here, motion ends here. Its initial position is the origin, its final position is this point, C. Now, question, calculate the work done by F on the particle as it moves along these 3 paths. What are they? First path, OAC. OAC. Okay, what's the work done if the object moves from O to C using this path? Part B, using this path. Part C, using this path. Okay. When we finish the calculation, we will compare them. If this is a conservative force, then all these numbers must be the same. Okay. Because that's the thing with conservative forces. When you move from a point, when an object moves from a point to another point, okay, if a conservative force is acting on it, then the path the object is moving there makes no difference, okay, in the potential energy. So let's find out. That will be the part D, okay, last question. So we will first do this calculation and then answer this question. Just like we already did, we will use this expression. Work done is F times delta, F times displacement. Since F is not constant, we need to integrate over infinitesimal displacements. And since this thing is happening in 2 dimensions, of course, we also do it in 1 dimension, but here it's like we have to use vectors, okay? And this scalar product. So it's like the more general form of the definition of work. Okay, so for the first path, OAC, here to here. We will do the calculation like this. We will divide this path to 2 parts, from O to A and A to C. And we will calculate them separately, okay? Simply because it's easier. First part is purely horizontal, second part is purely vertical. So in the first part, this dr will be I, okay, the unit vector times dx. In the second part, dr will be j times dy. Okay, so things are simpler. If you do otherwise, then it will be a more complicated integral. Here we go. This is how we split the integral. First from O to A, then O to C, and sum them. Just what I already said, these are the unit vectors in these two parts, okay? So, from O to A, integral is this. Force is here, 2yi plus x squared j dot I times dx. This dot is scalar vector product. Now, next thing we do the scalar multiplication. I dot I will give 1. I dot j will give 0. This term is cancelled. It's 0. Okay, why? Because perpendicular vectors give 0 when you scalar product them. So this integral will give 2y dx, okay? Y doesn't depend on x position, so it's a constant. It goes out. However, as you see, integral is taken from here to here, and along this path, y value is 0. See, because we are moving, we are integrating on the horizontal axis. So that integral is just 0. There you go. No work done in that part, O to A, from here as the object moves from here to here. Now the second part, A to C. Let's calculate. Here it is. In the vertical, 0 to 5 meter, j dy, okay? Now, j dot j will be 1. So that term survives. However, this term, I dot j, dies because I and j are perpendicular. Their scalar product is 0. Again, just like the previous integral, this x squared term, x itself, is a constant. X doesn't change as you move along purely vertical. Okay. However, x coordinate is not 0 in this case. Okay, it's not like the previous one. So let me show you. This integral becomes this x squared dy. Okay, x is a constant; it goes out. The integral is the integral of dy, so it's y from 5 meter to 0. So it will give 25, and x squared. The x coordinate was 5 meter, so that also gives a 25 meter squared. So it's like 25 to the power of 3. So this integral is 125 joules. So we finished path A. Total work done is 125 joules. Now we calculate for path B. It is, yeah, this blue path, okay? Like this. So we will do the same thing. Divide the path to 2 parts. Okay, so we split it. O to B, B to C. Then integrate. O to B, B to C. dr is j dy because O to B part is purely vertical. Okay. Again, x coordinate will be 0 there. Should we have any x terms? Here, the other path is this. horizontal part. So dr is I dx. Okay. Then let's write these integrals from O to B. Okay, the first vertical part, we have j dot j and j dot I, 0. I and j are perpendicular. This j dot j is 1. So this term, surrounding term, is x squared right here from 0 to 5. Okay. So this integral is 5x squared. However, x is 0 in that part from O to B, okay? Because we are moving exactly on the vertical axis. So that integral is 0. Work done is 0. The next part from B to C, we have this integral. I dot j 0. This 2y, I dot I is 2y dx, okay? 2y goes outside of the integral. It's constant throughout the integral. So this is x, and it will change from 0 to 5 meters. Y is non-zero. It's again 5 meters. So this is y, 5 meters, and this is the result of x integral. So work done is 50 joules. So if you move the object from in this path, the blue path, OBC, then work done is 50 joules. So in fact, we already have enough results to conclude that this is a non-conservative force, okay? Because the result of the first part was, it's already here, 125 joules. However, the other path gives only 50 joules. If you move the object through this path, the work done by this force is 125 joules. On the other hand, if you move the object through this path, okay, same force acts, but this time it does much less work, only 50 joules, okay? These are different values, so this force is non-conservative. Okay, now the final path directly from O to C, okay? Let's see how it's done. Here we go. Okay. In this path, we have dr as I dx plus j dy, okay? We also have x equals y. And of course, dx is also equal to dy, okay? X equals y because, see, it's diagonal. We are moving through the diagonal. Then, integral becomes this expression, okay? If you expand, keşke bir step daha yazsaymışım buraya. 2y dx plus x squared dy. You apply these in here. All, for example, you can say that all y's become x, like 2x dx plus x squared dx. Okay, shown here. And the integrals will run from 0 to 5. Okay, because that's the range of x. And here's the results, 66.7 joule. As you see, it's still different from the previous two results, okay? Therefore, this force is patently non-conservative. So, any questions so far? Ne kadar sorusu olan var mı? Next problem. So we have this force, 6I minus 2J Newton, acting on a particle that undergoes a displacement, okay. So find the work done by the force on the particle and the angle between F and delta R. Cool. First we calculate work and then the angle between F and delta R. To find this angle, we will use this feature of scalar product, okay? It's, okay, I'll show you. First we calculate the work. Forces are given in unit vector notation. We simply multiply them. Okay, 6I minus 2J dot 3i plus j. Expand it, okay? I dot I and j dot j terms survive. Those multiplications are 1. Cross multiplications I dot j are 0. They are perpendicular, okay? As shown in here. So work done is 16 joule, right here. Okay. Now let's find the angle between these two vectors, okay? See, the definition of work is F dot delta R, which is F times delta R times cosine theta, right? We can use this part to find the to access the angle theta. So this is like both a work energy question and the vectors question. We first need to evaluate the norm of these two vectors, F and delta R. These norms are 6.32 Newton and 3.16 Newton. Okay. Then put these values here. Put work 16 joule here. What you get is cosine of the angle theta. You calculate arc cosine, inverse function. Okay, so cosine is 0.8, which means that theta angle is 36.9 degree. Okay, next problem. So we have a single conservative force. Okay, it's conservative. Bu bir dakika, bu zaten çözüm soru değil mi? Evet, tekrardan şey olmuş. Tekrar etmiş soru. Tamam, bunu atlayalım. Bir tek ilave şurası var. Find VF. Okay, you can find the final velocity of this object. Hatta burayı geri kapatayım da şey olmasın. Tamam. Next question. So we have this ramp, okay, like this, and an object right here. There's a spring here. Spring is compressed initially for 10 centimeters. We are also given the stiffness of the spring. Then it's released. Object is released. Okay. When released, spring expands, losing some elastic potential energy, giving some kinetic energy to the object. Okay. Then object reaches this point, begins to ascend, go up the incline. Okay. What's the question? Using energy considerations, determine how far up the incline the block moves from its initial position before it stops. We are asked to find this number, D. Okay. For two cases, case 1, the ramp is frictionless. Case 2, there is a friction on the ramp, okay? Not in this part. This part is always frictionless, only on the ramp part. So let's find out. As I said, initially there is elastic potential energy, and finally there will be gravitational potential energy, okay? Initially object is at rest, finally it will again be at rest. This is just like one kind of energy being transferred to other kind of energy. Of course, if you define your system like this, object plus spring plus the earth or gravity, okay? You can speak about potential energy only if you include the relevant force in the system. So the system here is this: gravity or the earth, object, and spring. Now, the case of frictionless ramp first. So here it is. energy equation. This is an isolated system, okay? There is nothing external, no external forces. So changes in the energies must be zero, okay? No energy enters this system boundaries. Therefore, change in the kinetic energy plus change in the gravitational potential energy plus change in the elastic potential energy plus change in the internal energy, heat energy, must be zero. If one of these is decreasing, other ones must increase with the same amount of energy, okay? So, concerning the kinetic energy, no change. Initial kinetic energy is the same with the final kinetic energy, okay? Why? Simply because object was at rest, both initially and finally. Next, change in the gravitational potential energy. If we say that height of this height is zero, okay, then initial gravitational potential energy will be zero. Final gravitational potential energy will be this distance times mg. Okay, and this distance is just d times sine theta. D is what I'm trying to find. It's my unknown. Here it is, mg d sine theta. And d sine theta is h. So this is just mgh, final gravitational potential energy. And if you look at the elastic potential energy part, initially we have this much elastic potential energy. There's a certain compression on the spring of 10 centimeter. A spring constant is also known, so everything is known here, okay? Everything is known. Therefore, I can just simply solve for D and find my result. Here. mgd sine 60 minus 1/2 k xi squared equals 0. You can think about this result like this. Just put this elastic potential energy term to the opposite side of the equation, and you can say this. I had a certain amount of elastic potential energy in the beginning, which is transformed to this much of gravitational potential energy. Bu şekilde de yazabilirsiniz yani veya düşünebilirsiniz. Baştaki enerjiler bir tarafta, sondaki enerjiler eşitliğin öbür tarafında. Solve for D. Here it is, 4.12 meter. Okay. Here we had a sine 60, which is 2 over square root 3. And here's a triangle to help you remember those values, okay? When the angles of this right triangle are 30 degrees and 60 degrees. They are like this, 1, 2, square root 3. Okay. 1, 2, kök 3 diye gidiyor. Bu üçgeni de ezberleyebilirsiniz. Hatırlamakta yardım oluyor şeyde. Şu 30'lu 60'lı derece açıların trigonometrik şeylerini hatırlamakta. Okay. Next one. Next part, sorry, is to do the same calculation when there is friction, kinetic friction. In that case, we need to calculate the kinetic friction force, which will do work on the object as it travels this distance of d. So displacement is known. If I also find the kinetic friction force, I will just multiply it with this displacements and find how much energy went into heat. Okay, went to internal energy. Yani şeyi bulduğum an B kısmı da çözülmüş oluyor bu sürtünme kuvvetini. How do I find the friction force? I need the normal force, okay? So vertical forces, if you define your coordinates like this, this is the best choice because these coordinates align with motion. So this is normal force. This is the weight of the object. Therefore, the force balance of forces in the vertical direction, Fy, in fact this is Fy prime. Çünkü G üssü demişim burada. Bunlar farklı şeyler değil. There is no acceleration in this Y prime direction. So forces are in balance. N is equal to mg cosine theta, which is 0.980 Newton, normal force. Now I will multiply this with friction coefficient. There it is, the friction force. Multiply normal force with the friction coefficient, which is 0.4. This is the friction force, kinetic friction force, okay? Next is put this into the energy equation. Here this part is the same with the previous part, part A of the problem, okay? Change in the gravitational potential energy, change in the elastic potential energy, change in the internal energy of the system. So now, again, if you put this to the opposite side of the equation, you will see that now it's not equal to exactly to the gravitational potential energy, but there's also this term, the friction. Part of the initial energy must go to friction, heat. Let's see how much did. So again, solve for D, okay? This time there's the D term also here, so you need to solve them together. Here it is, mg sine 60 plus fk, okay? So this, if you look at this expression compared to the previous solution, there's this extra term at the denominator, so D will be smaller, okay? Here it is, 3.35 meters. Compared to the former result, it was 4.12 meters, okay? So as expected, when there's friction, particle, object goes to a smaller height. Daha az yükselebiliyor. Sürtünmeye gidiyor çünkü enerjisi. Okay. I think this is the last question. Zaten evet bir saat ders yapacağız, sonra bitecek. Last question. Moreover, there is this calculation, power, which I didn't lecture yet, but you'll see that it's very easy. I'll just do the calculation, and after you learn the concepts, you can also come back. I don't think that will be necessary. So, this object, its mass is 4 kilogram, and here we are given its position as a function of time. See, t plus 2t cube. This is interesting, t cube. So, this is the kind of motion in which acceleration isn't constant. Even acceleration is changing, okay? Because in motion with constant acceleration, that should be t square, right? You differentiate this twice with respect to time, then you will get acceleration. You will see that you still have a t term there. Yani iki kere türevi aldığınızda hala yine bir t kalacak. Ondan sonra hatta 12t yani tam nümerik olarak da. Hatta birazdan hesabı da var, evet. Neyse, fazla gevezelik yaptım, zaten hesaplayacağız. Anyway, what's the kinetic energy as a function of time? Here it is 1/2 mv square. Here v, speed is a function of time. We don't know speed, so we need to differentiate this once with respect to time. And we get this function, okay? We are asked the function. So velocity is this 1 plus 6t square. You put it into 1/2 mv square expression. So square it, multiply it with mass, divide it to 2. This is the kinetic energy. Okay, K, 1/2 mass, 1 plus 6t square squared. Kinetic energy. Part A, done. Part B, find the acceleration and the acting force. To find the acceleration, we will differentiate velocity, speed, with respect to time. Then this will cancel, 0. This will be 12t. And if acceleration is 12t, then I multiply it with mass and I will find the force using Newton's second law. Here, acceleration is the derivative of velocity with respect to time. It's 12t. Force is acceleration multiplied by mass. Okay, so it is 4 times 12t, 48t. Okay, this is like that's the calculus sort of problem. And finally, find the power in this of energy transfer to the system. Let me quickly define what power is. Power is the rate with which work is done on an object. Okay, so it is basically delta W divided by delta T. Sorry, W divided by delta T. Yani birim zamanda kaç jülük iş yaptığınızı gösteren şeye güç deniyor. Sayıya, ifadeye. Work'i alıp zamana bölüyorsunuz, o kadar. 48T. Bir de şey kısmı var tabii. Bir ifadesi var, onu aşağıda göstereceğim. So, find power is, you just differentiate work with respect to time. Okay. dW divided by dt. Now, what is work? It is kinetic energy because of work kinetic energy theorem. Since the only thing affected in this system is, by the way, just the object itself, okay? There is not even a mention of a force, right, in the question, so I can't say that there's, or I don't need it. So, this is dk over dt. We differentiate the kinetic energy with respect to time to find work. Okay, so here's it, 48t plus 288t cubed. That's the power. It's this many joules of energy is transferred to this object every second. Finally, find work done on this object in this time interval from 0 to 2 seconds. So here we go. Since work kinetic energy says that kf minus ki, the difference in kinetic energy is the work done on the object, then this is the second expression I just mentioned. Power is also equal to force times velocity. Okay, derivations will be shown in the class. So we multiply, we will find power as a function of time. That's the multiplication. Therefore, bu şey tabii de baştaki kinetik enerjinin 2 joule olması durum var. Onu ama bize burada tam verilmemiş. Şeyde eksiklik var. Sıfırdan 2 saniyeye. Okay. This is forgotten, okay, in the question part here. It should be actually here. Initial kinetic energy of this object is 2 joules, okay? Then the final kinetic energy is kinetic energy of the object at t equals 2 seconds minus this initial one, okay? Which will give me the total work done in this time interval, and it is 1,248 joules. So we finished solving problems.